Okay, so it's time to start. I would like to welcome you to a new edition of the TUCS Distinguished Lecture Series. It's my great pleasure to introduce Johan Håstad. He's a professor in computer science at the Royal Institute of Technology in Stockholm, Sweden. He received his Bachelor of Science from Stockholm University in 1981, his Master of Science from Uppsala University in 1984, and his PhD from MIT in 1986 under supervision of Shafi Goldwasser. He was appointed Associate Professor at the Royal Institute of Technology in Sweden in 1988 and obtained a full professorship at the same place in 1992. He also held visiting positions at MIT and at the Princeton Institute for Advanced Study. He is a member of the Swedish Royal Academy of Sciences since 2001 and a Fellow of the American Mathematical Society since 2012. Johan Håstad has research interests within several sub-areas of the theory of algorithms and complexity theory, in particular complexity theory, lower bounds, cryptography, and pseudo-randomness, randomized algorithms, and approximation algorithms. He has in recent years mainly focused on the approximability of NP hard optimization problems. Johan Håstad was the recipient of the Gödel Prize in 1994 and again in 2011. He was also the recipient of the ACM Doctoral Dissertation Award in 1986, of the Göran Gustafsson Prize in Mathematics in 1999, of the Chester Carlson Research Prize in 1994. He was an invited speaker at the International Congress of Mathematicians in 1998 and a plenary speaker at the European Congress of Mathematicians in 2004. It's a great pleasure to have Johan here, so without further ado, I give you the floor.
Thank you. Thank you very much for this introduction, and it's a pleasure to be here. And yeah, life is long, what can I say? Yeah. So what I'm trying to do, so first of all, I had some recent dentist surgeries. I'll sometimes have a problem pronouncing some things, but I'll try to do my best. So I'm not going to really tell you about some recent things. I'm going to just tell you about some things I like. Some of them are recent and some are not so recent. And in Sweden, we think the Finns are more quiet than the Swedes, and if you prove me wrong, I would be happy. So please ask questions and whatever comes to mind. So broadly speaking, what am I interested in? Well, I'm interested in efficient computation, and that actually has a lot of practical things. If you're in a big city and you sort of say, I want to go from point A to point B in your computer, you really want the computer to answer even if you're in Paris or some other place in a second. And this is just sort of just the basic algorithmic questions that we assume that computers can solve, and it's easy to check that it actually does it. Sometimes there are very bad implementations and you get very bad suggestions, but that's a different story. But in principle, this is easy to solve. A more interesting question these days is, that we don't know the answer to, and AES is the advanced encryption standard. Okay. That's better. And AES encryption is one of the standard encryption algorithms that's used on the internet, and the question whether thousands of PCs can break such encryption in a year is a question that we don't know the answer to, and then that gives rumors in the press. I don't know if that kind of rumors made it here. Yeah. But practice is one thing, and I'm mostly a theoretician. And in theory, we sort of interested in the basic question. I give you a computational problem. How difficult is it? And the way I'm going to measure difficulty is sort of how many operations you want as the function of the input size. So let's take a simple example here to get up to speed. We're multiplying numbers, and the question is how difficult is multiplication? And we're multiplying n-digit numbers. Okay, and I just did this the way at least we in Sweden were taught to do it for n equal to 5. And if you sort of think about it, this takes about 4n squared simple operations, where a simple operation is a multiplication of two one-digit numbers or addition of two one-digit numbers. And the first thing you should ask yourself, is this the best way to do it? And the answer to this is pretty simple. Yeah, of course it's the best way to do it. We have n digits in one number, we have n digits in the other number. And of course, you have to multiply each digit in one number by each digit in the other number, right? How many believe that argument? You nodded, you confess. Right? It's sort of, yeah, you can sort of pass me. This is a completely bogus argument, of course, right? And there are much more efficient ways to do multiplication. And it's sort of such a nice to explain problem that it's really one of my favorites. And I'm not really going to tell you how you do it, but I'm just for... In fact, you should really think as a number as a vector of digits. And then once you realize that, you know, multiplication is essentially convolution, if you know what convolution is. And then you realize, well, you know, the fast Fourier transform is an excellent tool, so you should do the fast Fourier transform, and then you figure it out. Okay. So, and this was originally done by Schoenhagen and Strassen in the 70s, and they were sort of the champions with the quickest multiplication algorithm for a long time. And Martin Fourier quite recently slightly improved, so I'm saying here slightly more than n log n. So for those interested in details, this is, you know, n log n times 2 to the log star, if you know what log star is. And that took away a log factor that existed from Schoenhagen-Strassen. But this was at least an improvement of a running time that existed for 35 years. But something I really want to point out for you who haven't seen, if I ask you the question, can we do multiplication with 10n operations, you know? Can we do multiplications approximately as easy we can do addition? The answer to this question is we don't know. Okay. So there are algorithms that's much more efficient than, you know, the things we were taught in school. They roughly work in n log n, but we don't know that they can't be done even more efficiently. So if you don't have anything more useful to do, you can think about multiplication for the rest of this talk, or go home and think about it afterwards. Because if you break this n log n barrier, you would be really world famous immediately, and you have all the tools there, right? You can just go home and think. Okay. So this, my old advisor Lennart Carlsson in Sweden says that, you know, computer science didn't get out of grade school yet, and maybe we didn't. So that. But for most of this talk, I'll take a different setting and saying that polynomial time is actually good. So some polynomials are better than others. This is an unusually bad polynomial. And exponential time is bad, and this is, you know, of course, much worse than this. But the point is being that, you know, exponential will always win in the long run. If you have an exponential time algorithm, if you're going to run it on large inputs, you won't have enough time. And here I'll take one of the favorite problems, which is the Traveling Salesman Problem. So you have a salesman that wants to visit 100 cities in Sweden, and he wants to travel as little as possible. And we'll think of n as the number of cities, but you can think of it as 100. And something that's sort of funny from a mental point of view is if you sort of say that, well, let's find the smallest tour with Stockholm, Göteborg, Luleå, Uppsala, and Malmö. That's sort of trivial on the previous picture, right? If I put these, maybe not all of you know where all these cities are, but once you made it into a digital table, it suddenly gets a little bit more difficult. But it's easy here. You can try all these orderings, and in fact, you should go from Stockholm to Uppsala to Luleå to Gothenburg to Malmö and then back to Stockholm. That's the best way to do it. And so of course now if we have 100 cities and we want to try all possibilities, it gets a little complicated. And the number of possibilities, you have 99 for the first city and 98 for the next city and so forth. So in total we have this number of possibilities. And then you lazily think that this is a large number of possibilities, but when you actually write it out, you realize that this is actually a really large number of possibilities, right? You're not doing too well on the question part so far, by the way, but I suppose everything I said was clear. So this is 99 factorial, a fairly big number of possibilities. And well, we're sort of gleaming a little bit on practical computing. Computers are pretty fast, and they do about these days 1 billion operations a second. And this means that even a stupid program will solve a traveling salesman instance with 14 cities in about 1 second. But as you might have noticed from the previous slide, it won't, for 100 cities, there's nowhere near what you can do. So let's see how your understanding of numbers is. Will you live 1 billion seconds? How many people believe that they will live 1 billion seconds? How many people believe that you won't live 1 billion seconds?
American or European?
I got as I was pointed out, I turned into an American when I was, so this is 10 to the 9. But you should have discovered this already from the first line, right? How much is 1 billion seconds? You know, what's 1 billion? This is 10 to the 9. So it's about 30 years. So we live a few billion seconds, actually. But 1 billion pretty fast. So one famous quote is by Knuth that says a premature optimization is the root of all evil, but billions go away pretty fast. So one thing I like to say is that complete absence of optimization might be even worse. So let's return to trying to make things quicker. So a very classical algorithm by dynamic programming that you might, if you know what dynamic programming is, that's good, and if you don't, it doesn't really matter, but you can just realize that there's some technique that will make traveling salesman go significantly faster. So instead of n factorial, you'll have basically 2 to the n. And this sort of increases 14 to 25, but the 100 city instance is really nowhere near to be. And then, of course, you sit back and think about it and say, well, is this possibly the best we can do? And the answer to this is, well, we don't know. And in fact, you would essentially want to say that, you know, TSP is a difficult problem, but we can't prove that you require more time than actually reading the input. So here, since we have n cities, we have n squared pairs of distances, and you can't prove that to solve TSP you need more work than actually just reading the input. Okay. Well, it seems to be a very difficult problem. So the way we were sort of trying to make progress on this problem in the early 70s is when Cook defined the NP-complete problems. And this turns out, how many know about NP-complete problems and are very familiar with them? How many people have not seen the word NP-complete before? Okay. So maybe I shouldn't preach this. So this is a set of problems. How you define them is not so important. That we can't prove that they're solvable not solvable in polynomial time, but everybody believes so. And NP versus P is $1 million question, literally, and eternal fame, and and it has lots of candidates. So almost all interesting combinatorial problems turn out to be NP-complete. And take your favorite problems, and I listed a few, and Traveling Salesman Problem is one. Yeah. So first I want to say that I started my career in complexity theory, and the thing I really wanted to do when I was 22 years old is to prove that NP is not equal to P. And then I was starting to try to prove some lower bounds, but I never got very far. And somehow it seems like the entire community has given up. We are nowhere near proving that NP is not equal to P. That would require to model arbitrary computation and tell. It's very hard to prove that things cannot be done, and it seems like we're making very little progress there. So what sort of has more and more come into the play is to say, well, let's assume this is the case and let's derive consequences. It's like physicists, more or less. We assume the world is like this and we're going to work according to it, and that's the way things are. Yeah. So one thing I like here is this definition, I don't know if this defines reasonable researcher as a statement about the world. You know, you can sort of make it true by as a tautology by saying that everybody doesn't believe the same way I do is not reasonable, but that's a different problem. So sometimes you can wake up at night and say, you know, what happens? Suppose NP is really equal to P. And by really equal, it doesn't mean that Traveling Salesman has an algorithm that runs in n to the 100. It means that any NP-complete problem really has an algorithm that runs really fast. Okay? So you can run it in practice. So for instance, all planning problems are easy. You know, it's great. If there is a good solutions to be found there, you'll find it as quickly as to check it. So now not so worrisome nice aspect is that, you know, for mathematical theorems, it will be as easy to verify the proof as to find it, which basically says that mathematicians will be out of a job, which some of us think would be boring, but society in general would sort of might be happy with, because one less to pay things. But something that more worrying me from practice is that would essentially be no security or privacy on the internet. It would be very hard to make secure communication, and this would actually be a very negative impact on mankind. So the fact that they're not equal is a mixed blessing, and we have to live with the world that we have. But now we're theoreticians. So, and we have to prove theorems, so we want to prove theorems about the NP-complete problems. And we're back to our favorite problem, TSP. And now we sort of can say, well, NP is not equal to P. That's the way we view nature. So now we're into looking at algorithms that always finds the best solution and sometimes are slow, or algorithms that are always fast and find reasonably good solutions. And you can sort of make interesting theory about both these, but I'm mostly interested in two: approximation algorithms. You know, we want to find an algorithm that always is fast and always finds a reasonably good solution. So for TSP, sort of a very everyday life is very much like a planning problem, and we all know how we solve problems in everyday life. You take the cheapest thing for, you know, the next thing you have to do. Locally optimal things, which for TSP is called nearest neighbor. You go to the closest city which you haven't visited so far. Okay. So it's easy, you know, it's reasonable, it's easy to calculate. It sort of does reasonably well, but question, you know, can we prove some mathematical theorems about this? So let me first tell you what it is. Well, here we have some points in the plane I want to visit. And, you know, if you each time go to the closest place, then you'll sort of go far away and then you have a long trip back. And it's clear that here is a much better solution for this instance. So this sort of says that nearest neighbor doesn't always work. But this is not a very sophisticated statement. So the way we turn this into mathematics is to say, well, let's look what the cost is of the found solution. Let's divide it by the optimal solution and see how well can we do. So the quality of a heuristic, we want it to be fast, but then really the quality of how well it performs is the worst case ratio on what we find compared to what we could have found. And now we can start proving lots of theorems for lots of heuristics. And if you look at the greedy heuristic, you can make a mathematical proof that says whatever input we have, you know, if it's planar or not, we can come within a factor which is a constant times the logarithm of the number of cities. And then you want to complement by this saying, well, there are some bad instances where in fact you can be off by a factor of log n. If you're sort of greedy, over time you'll spend another constant times log n. You'll travel by a factor of log n more than you could have done optimally. You're happy with this definition? Any comments, questions? Anybody? Everybody's happy. Great. So this is the sort of jargon way of saying this is a theta log n approximation algorithm. You know, it's within log n, one constant log n. It's also off by log n, and theta log n is that it's sort of log n. That's the right order of magnitude. And the first thing you should do when looking at an algorithm is that, well, we want to be in a constant. You know, we really want to be within 1% or 10% or at least a factor of 2 of the optimal. And the question, is there an efficient algorithm that gives you within a factor that's independent on the number of cities, you know, that doesn't grow with the number of cities? And this, before somehow even the idea of an approximation was discovered, Christofides in 1976 says, well, there's a very nice algorithm that always gives us within a factor of 1.5, you know, 50% more than the optimal solution. And what it does, I don't know if it finds a min-cost spanning tree. I'll have pictures on this, and then, well, so here's a graph. So somehow you want to connect. So what you do first is you find a spanning tree that sort of just connects all in the cheapest possible way. And this turns out to be an extremely easy operation. You know, it's a very efficient algorithm. And this doesn't very much look like a tour. In particular, the guys of degree 1 are sort of bad, because something in a tour you have to leave from a tour also. And it turns out that, in fact, also the guys of degree 3 are bad, but that doesn't matter. So what you do is you take the guys of degree 1 and you add a minimum matching on these guys, which is also an efficient algorithm. And then you, in fact, have something that's fairly tour-like, apart from some places being visited too many times. And what you simply do is you take a shortcut on these, and that just makes the things shorter. And that gives a 1.5 approximation algorithm. This is sort of a classical 1.5 approximation algorithm from soon 40 years ago. Okay. So the natural question now is, of course, is this the best we can do? We have within one factor 1.5. Can we get, you know, within 20%? Can we get in within 10%? Maybe, well, maybe moderate 49%. And nobody has been able to beat this for the last 38 years. So the first approximation algorithm, more or less, gives 1.5, and nobody has been able to beat this in general. So this is another open problem you can go home and think about. I mean, all the things are there, right? That you have a set of cities, you want to visit them all, and you just want to make sure that you're not off by more than... but I need to tell you something, is that don't think too much about the plane where my example lived, because in the plane you can do within any constant. You can get within 10%, you can get within 5%, and you can get within 1%, and these were two independent in 98 that sort of, after 22 years, realized that you could use the geometry of the plane to get something that's better. So the only thing you should use to get 49% is the triangle inequality. That's the only thing you know about the distances. If you're going from A to C, it never is, you don't never win by going via another city, which is sort of the natural thing. Okay? Yes?
One question, so I'll ask, is this fully polynomial? Is the approximation sheet fully polynomial?
No, so if you want to get within 1 plus epsilon, epsilon goes into the exponent. Okay. I actually was interested in these algorithms and I had a master thesis student who wanted some programming project and was supposed to program this thing, and it's not so fast in practice. But we're doing theory now for a while. Thank you. So sorry, now I forgot. The question was whether this is fully polynomial. I'm supposed to repeat the questions for the tape. So the next thing you want to prove is that, well, maybe 1.5 is the best possible. Maybe Christofides was so sort of heads on that he got the best constant in the first shot. And here we sort of, if NP is equal to P, then in fact you can do it optimally, but that's our view of the world, that NP is not equal to P. So we'll assume that NP is not equal to P and then prove statements based on this view of the world. And here there has been, lots and lots of progress on various problems. And the progress on TSP is a little bit modest. It's like you can't do it better than within 1%. Okay, so there's still between 1 and 50% off. That's yeah. So now I want to switch to, maybe we've seen enough of TSP, and I want to switch to another topic, and that's sort of the Boolean satisfiability. And it's sort of, we have Boolean variables that are true or false, we have negations, and we have and or. Yeah, I don't know how. And if you're just a small example, if x1 is the probability, is the event that Alice drives on the left-hand side going east, and x2 is the event that Bob drives on the left-hand side going, well, the first was west and the other one was east, then in fact no collisions, they should all both abide by the rules of England or by the rules of Sweden. They should both be on the left or both be on the right, and then we're fine. Then for those who are sort of interpreting small logical formulas, this is logically the same as this, but this is much harder to convince somebody that this is saying the same thing. So somehow humans can't really parse logical formulas of size 4, which is a little bit disappointing. So let's take the most favorite problem of logical formulas, which is sort of 3-sat. And let's see how, I'm always uncertain. How many people know whether 3-sat is an NP-complete problem or not? How many people don't know the answer to this question? There's a pair that don't know. Okay, good. So so the question is, can you find the logic? Can you find some assignment that satisfies? These are ORs, right? So you want an assignment such that x1, x2, or x3 is true, and so forth. And the question, can you satisfy all these constraints? And it's easy to check here that this is in fact a satisfying assignment. If you go over all these 12 clauses, as they're called, these disjunctions, they're all true under this assignment. And the classical question of satisfiability, this is called SAT or satisfiability. And this typical variant I had, this is called the 3CNF formula. 3 is the number of variables or negation in each clause, and it's conjunctive normal form, which is just saying that these are conjunctions. This is the 3-sat, and this is the first NP-complete. This is sort of the mother of NP-complete problems. It's the problems, one of the problems that were first proved NP-complete by Cook in 1971. Yeah. But also here we get an approximation problem that I originally didn't like, but now I like very much. And it's, suppose these are constraints that really says things I want to be true in the world. Okay. So the question is, well, maybe, so that this is NP-complete is that you can't find a state of the world that actually makes everything you want to be true in the world true, but maybe you can make sure as many of the things you want to be true in the world are true. So let's try to in fact, satisfy as many of the constraints as possible. And suppose I even guarantee you that there is a perfect world out there where everything you want is fulfilled, that all these conditions are fulfilled. And now you want to satisfy as many of the constraints as possible. Okay? Are you happy with this problem? So any ideas? How would you do it? How many constraints could you roughly satisfy? Yes?
Half.
How do you satisfy half?
You take something that satisfies as many as possible. One of the variables which satisfies at least half of the things where it appears.
Yes, so you can take the x1, and if it's more positive than negated, you set it true, and otherwise you set it false, and you repeat this. Yeah, but half is. But then if you satisfy, if you set x1 equal to true here, which sort of looks, it has two appearances as positive and two as negative. You satisfy these two guys, but still, this has still two shots, right? Right, because this is already true because we know that x1 or x2 or x3 should be true. Yeah, things in that sort of how poorly can you do in this world, or what sort of get the benchmark. Let's not look at the formula at all. Okay, Let's just flip a random coin for each variable and decide if it's true or false. Okay, that's just to get a feeling for how poorly things can be. And then if you sort of just randomly flip, you can look at the clause, you have sort of 3 shots of making it true, right? If x1 turns out to be true, you're fine. If x2 turns out to be true, you're fine. And so in fact, that case you will satisfy each clause with probability 7/8 because you have 3 shots and each happen with probability 1/8. You have to be unlucky 3 times in a row, which is 1/8. Okay. So the surprising fact is that this is the best you can do if NP is not equal to P. If I give you a big complicated formula, there's no way, systematic way to beat 7/8. If I ask you to beat it by getting 0.876 instead of 0.875, that's an NP hard problem. So if you could do that efficiently, NP is equal to P. So 3-sat formulas are really too complicated for efficient computation to understand. The best you can do is give up, flip the variables at random, and hope to maybe you're a little bit luckier and get something a little bit above 7/8, but that's really the best we can do. Yes?
How much harder is it if you have like weights for each of the clauses with the preferences?
So the question is if you have weights for the clauses that change it, and the answer is no. It's still 7/8. The algorithm will give 7/8 still because it doesn't look at the weight, so you'll satisfy 7/8 on the average. And so it doesn't get harder in that sense, and it doesn't get easier either. Thank you. So the point is what I was just trying to say, that 3-sat is really too complicated. Yes?
Sorry, I guess what you said now it puts this problem in ZP.
Which problem? To get 7/8.
Yeah, to get 7/8.
Yeah. So you can do it. The question is this in CP, which is a probabilistic CPP, I think it's called, right?
ZP,
Yeah. It's a probabilistic complexity class, and the question. So the answer, the question you might be able to, you can also do it deterministically quite easily. That's a good exercise for your homework problems. You don't think about it now. You can think about it after the lecture. Yes. So let's do something really, really simpler, okay? So let's stick with Boolean variables, but the only thing we'll ask is that 2 variables are not the same, okay? I say, x7 should not be equal to x27, and x8 should not be equal to x9, but these are the only conditions I'll have. Lot simpler. So let's see if you can, what fraction of the constraints will I satisfy if I just don't look at the formula now and do it randomly? I just flip random value. I have, a million variables, I have 10 million constraints of non-equality. How many will I satisfy on the average if I just flip random values for the variables? Half, right? Because you have 2 things and they're equal with probability 1/2 and unequal with probability 1/2. Okay. So let's, first of all, I've forgotten about this slide. So max cut is a different problem. I'm sort of giving you a graph with some connections, and the question is to divide this into 2 sets to cut as many edges as possible. And here I did this, I made some of them red, and I tried to cut as many as possible. Does this have any familiarity with any other problem you've seen in your life? Okay. It's the same problem, right? It's really the unequal problem, because if I think of xi being true as the ith node being red, having different colors at the 2 endpoints of an edge is exactly the same thing as 2 variables not being the same, right? So it's much more easier to think about it as a graph. It was sort of like in the TSP. It's easier to look at the map than just a list of things. And here it's sort of nicer to think of max cut as the unequal problem. If you didn't get that, just think about the max cut. So here it's actually easy. If I promise you that there's a way to cut all the edges, it's sort of very easy to find that cut. So the way to think here in approximation, if you can cut 99% of the edges, we can do it randomly and get a half. But the question is, can we do better? And the point is here that here we actually can do a lot better. And this is sort of one of the most beautiful algorithms that really show the new idea to use something. So I want to tell you a little bit about this algorithm. Okay? So if you sort of think about it in mathematical terms and sort of, and this is equal to seeing the unequal, let's use plus and minus 1 as the things that are supposed to be equal or non-equal. Then if you look at the number of edges and you look at this quantity, this is exactly the number of satisfied constraints, or sort of the number of cut edges. Because this product is 1 when they're equal and minus 1 when they're not equal, so you just really sum up the number. So Grammans and Williamson really said, well, let's make life simpler. Let's replace this variable by a new variable, and now it's much easier to optimize, right? You can all optimize this thing. Because we don't, I mean, now we sort of don't have, I mean, each variable just appears once. It's not hard to optimize this, right? But what really they said is that the way we want to optimize this is that the y's here form a positive semi-definite matrix which has ones on the diagonal. Okay. So if you think about the xij's, in fact, whatever they will do is that the corresponding y's, yij's, which should be equal to this, will be a positive semi-definite matrix. And what's a positive semi-definite? Well, it's symmetric also. Well, it turns out to be equivalent with a couple of conditions. One is that it has positive non-negative eigenvalues, that the quadratic form is positive, or that it factorizes as V transpose times V for some matrix V. This is all. And in fact, the sort of intended solution is just the outer product of two vectors, which is a special case of this thing. And the main sort of insight is to say that if we sort of generalize it in this way, it turns out that you can optimize over positive semi-definite matrices. Okay. And this, I'm not going to go into this. This happens because that's a convex set, and you're optimizing a linear function over a convex set, so there are no local minima, and in fact, some type of steepest descent will do it for you. But that's. But behind this, one way to look at it is that you started this problem, and if you really think of y as a product of a matrix V transpose V, this really says that instead of having these plus minus 1 variables, we are looking for a vector solution where these products are replaced by the inner product. While this is an NP-complete problem to maximize this is polynomial time, because you're sort of interpolating between plus minus 1 in an efficient way. And sort of looking back, what have you done? Well, we've done a vector problem. So you've sort of, one-dimensional vectors are special cases of vectors, so we sort of made a more general set of solutions. And the key question is how to, when we get the vector solution, we want the plus minus 1 solution back. And here's another key insight of Grammans-Williamson, is you have a vector solution, with vectors that live in n-dimensional space. You'll just pick a random hyperplane and use that for rounding. Okay. If you're seeing this for the first time, it's hard to digest. I'm not getting too many happy nods, so I'll soon get out of this. So you analyze this. Let's not worry about it. But in the end, you can prove that this algorithm, that you find the vectors, you do this rounding with the hyperplane, will get you the answer within a factor of 0.8785. And this function is actually the minimum of this function between, over an angle theta between two vectors. Okay. So it's a very, how many people have seen the Grammans-Williamson algorithm before? Nobody really, okay. So it's really a fantastic algorithm. Go home, look at it. The idea is you have Boolean values plus minus 1, and we want to relax them to vectors in Rn. and then you can get back an integer solution. And this actually beats taking a random solution. And this is the mother of lots and lots of algorithms. Okay. So this is as technical as it got. I mean, anybody wants to ask a question about this? I'll try to. Yes.
What's the name?
So this Michel Goemans and David Williamson. This is from 95 or something. And it has, hundreds of, it has been applied, semi-definite programming has been applied to hundreds of problems. So it's really a killer method for future things to get approximation algorithms. You can, semi-definite programming in Google will give it to you. Okay. So now you've got this sort of very strange number. You have this very simple problem max cut, and you got an algorithm that had a very, the approximation ratio was a very complex. It was an optimization problem involving some trigonometric functions. You got a strange number, and you can sort of wonder: is this possibly the best approximation factor that can be gotten by any polynomial time algorithm? And in fact, I had the result from 2001 that you can't do this within 0.941. And then in 2004. Some people Kindler, Mussel, and O'Donnell proved that if the unique games conjecture is true, then the Goemans-Williamson constant is correct. Okay. And this doesn't make much sense to you, but I'll tell you a sort of a washed-up form of the unique games conjecture, which is another problem you can think about. Okay. So it's also very simple. So I give you linear equations, but they're modular equations. So we just care about the answer mod m. And they're simple of the form that it's just of the form that the difference between two variables is a constant. So I say you that x3 should be x1 plus 11, and then I give you a system of these equations. Okay. And of course, if I tell you that you can solve all these equations, it's very easy to find a solution. You just, you fix any value for x1, and then you know the value for x3 and x4, and then you know the value for x2, and so forth. So if I guarantee you can satisfy all the equations, it's a very easy one. But the question is, suppose I only guarantee you that there's a solution that satisfies 99% of these equations. Okay? Then in fact, it's hard to find something that does exactly 99%. So I'll ask you to do less. Can you do something that satisfies 1%? Okay. And the unique games conjecture says that you can't do this for sufficiently large modulus. And for 99, any number less than 100, and 1, any number bigger than 0. Okay. That even equations of this very simple form, if you don't satisfy all the equations, but just almost all the equations, it's in fact hard to get something that satisfies a substantial fraction of the equations. So this is also a very simple mathematical theorem to think about. And this is a very interesting open problem whether this is possible or not, because people's opinions are divided. It's not clear if it's going to be true or false. Yeah. So it seems like it's hard to make instances which are difficult. It's hard to make an algorithm. There are lots of interesting algorithms proposed, and this is really a topic for future research. So am I doing? Well, I'll give you one small last piece of. So Traveling Salesman. The question is which constants in this world do we mathematicians need to calculate? I said that TSP you can approximate within 1.5, and it's hard between 1 to 123 or 122. So many people say, well, it's within a constant. Who cares what this constant really is, right? It's a constant of nature. We won't know all constants of nature. Let's not worry about it. I like constants, by the way. I think we should know it, but that's a different story. So let's look at the sort of a very, very related problem, and that's Traveling Salesman Problem, where it might be easier to go from A to B than B to A. We have downhills, we have uphills, we have headwinds, we have tailwinds. So this is sort of a hill here to signify that, you know, that it might be easier to go up than down. And then, in fact, this algorithm doesn't work anymore, as Christopher said. And then, in fact, the best algorithm are almost as bad as the algorithms I told as nearest neighbor. You can get the best algorithms gives you within log n over log n, and the lower bounds gets a little bit. So it's hard to do now over 75 over 74. So somehow it's harder to prove hardness than algorithms, so maybe it's a constant. But here's an unusually embarrassing. Heldenkarp in the 70s suggested an approach to a linear program that would in fact solve traveling salesman problems. And as far as we know, it's within a factor of 2 of all instances. It might be that this particular algorithm is never off by a factor more than 2, but we can't prove that it's off by any particular constant, and we can't even prove that it beats log n over log n. So this is another open problem, you know. This particular algorithm, or any algorithm for the asymmetric traveling salesman, is cool, but it's more difficult to go one way and the other. This is also something to think about. So what I wanted to say is that, so for max 3-sat, you know, satisfying as many constraints, we really had that the trivial algorithm gives you the optimal ratio. For max cut, we have if the unique games conjecture is true, then we know what the optimal constant is, and it's this strange number. But if it's unique games conjecture is false, it's still very much open. Asymmetric TSP, we don't know the answer even if we're assuming the unique games conjecture, so it's very uncertain what the true answer is. So I think this is a very exciting set of questions. You know, lots of them can be stated very simply, and if you feel like it, you can sort of go home and think about it, and that's the end.
All right, we should give our guest Are there any questions or comments or answers to our problem?
No answer. Question. NP equals P equals NP. Does quantum computing have any bearing on this?
So the question is whether quantum computing has any bearing on NP equal to P. And well, it's a very interesting question whether quantum computers can solve NP-complete problems. We don't know, right? We don't know that classical computers can solve NP-complete problems in polynomial time. So, of course, quantum computers are better. I mean, people have been thinking about this question for 15 years and couldn't come up with any algorithms.
So there's no obvious answer to this?
There's no obvious answer, yeah. No, if the answer was yes, you know, we might have found an algorithm. But if the answer is no, or if, I don't know. It's a good question.
Maybe one of the most opinionated guys on this stuff is Scott Aronson, if you know his stuff. I think he believes that quantum computation gives you something that's stronger than polynomial, but not as strong as NP, and randomization gives you P.
Yeah, so it was a statement that Scott Aronson, which is one of the opinionated people in quantum computing, thinks the answer is no. but this, yeah, it's also an interesting question whether randomness buys you anything in context, and there I think the general consensus is probably not. That P is in fact equal to BPP, that randomness does not, yeah.
Okay, one more question. So there was pi in the weird constant for max cut.
Yes.
It's an irrational number?
Or this I don't know. So this number is a minimization problem, right? And it would be extremely surprising if this was not an irrational number, but I don't know any proof that it's not a rational number. I mean, there's some general, I don't know this, there's some general theorems when cosine stuff can be even algebraic, but I don't know the answer to that question. Yes?
About the proofs about the hardness of approximation and some lower bounds for the constants. Is there some common technique for proving this stuff, or are they all different?
Sure. The question is if there's a common technique for proving lower bounds. And yeah, there's really another I could talk about called probabilistically checkable proofs, but intimately connected. So this is this concept, I can just say what they are. So in NP, you have sort of a traditional prover that writes down a written proof and a verifier that really works all over the entire proof and is convinced with 100% reliability. So in a probabilistically checkable proof, the prover still writes a written proof, but the verifier does what most proof checkers does. It checks a few random places. And the point is now that there's a probabilistic. There are PCPs for any NP language where the verifier just reads a constant number of bits dependent on the size of the proof, and still is only fooled with a small constant probability. And these translate to lower bounds in the sense that you need to model the cheating prover. Once we're down to, like students, right? I mean, they don't want to get the problem right. They just want the verifier, in this case the professor correcting the exam, to accept. So you might as well try to simulate the correcting professor instead of getting the answer right. And this sort of way of thinking also works in the optimization. And it's an optimization problem how to cheat the verifier. And that sort of turns into these lower bound results. So PCPs is the code word there.
Other questions?
I was intrigued by the question here about spiders. Is there any reason that in this kind of lower bounds that there will be a preference to get irrational lower bounds? There's nothing which...
No, the question is there preference to have rational numbers? And the answer is no, not really.
Inherent in the problem statement, which kind of gives you rational.
I mean, maybe before Gummans-Williamson we would have thought so, that you should get rational numbers, but here the analysis is actually quite simple. And it's you're comparing these two probabilities, that you have two vectors, and you want to compare the probability that when you use the rounding, that the rounding is the same, compared to their contribution to the objective function. One has cosine in it, and the other one has pi, and you take the ratio. And yeah, why not? Why rational? I don't see any philosophical reasons. Yeah.
Very generally, this approximation means how far you get from the optimal solution.
Yes.
Right? In the worst case.
Yes.
But what about the average case? For example, if we...
Yeah, no, that's also an excellent question. So the question is, I'm all doing worst case, how about the average case? Do I have a theory there? And this also goes for algorithm that always finds the optimum. You can look at the running time as, why do worst case running time as you traditionally do with NP versus P, right? It's much more profitable to look at average running time because that's what happens in practice. And there's some theory to this, but it's sort of not very, then the question, what probability distributions are we interested in, right? What's the natural probability distribution in any of our favorite problems? And then you can say, well, take TSP. I mean, you can say, what's random points in the plane or random metric in some... There's an NP-completeness theory with respect to distributions that Levin did in the 70s already. That sort of said, then the problem is not only an NP problem, it's an NP problem together with the probability distribution on instances. Okay, and then the question is, what probability distributions do you allow? Well, if you allow incredibly complicated probability distributions, then in fact you can diagonalize over worst case things, and this thing turns into worst case instances. Okay, and then he had two definitions. One was, do you want this probability distribution to be generated efficiently, or even that the distributional functions should be computed efficiently. Namely, what's the probability that you get, let's say, an integer that's smaller than this number? And then you were sort of trying to prove completeness results there. And you were able to prove some completeness results there. But that didn't turn out a very satisfying theory because it were very few complete problems. They were very artificial. And now you can try this with approximation algorithms also, and things get even hairier. But there are some very standard problems where people sort of like, random three-set formula, for instance. Can you do something? And where you really pick clauses at random has been studied a lot. That's right. So I pick, three variables at random. I may negate them randomly, and the question, can you do something interesting there? And that's been studied a lot. But it's sort of a little bit delicate balance what kind of questions we want to study and getting a satisfying theory out of it. So yeah, so you can study it, but there's no really there are no nice mathematical answers, but there's a lot of practice out there.
Any other questions? If not, then we should thank you once again for a great lecture.
Thank you.